Hi, Eric. How are you? Hi, Cameron and Carlos. Carlos is connecting. Okay, we'll start in a few minutes. So check out the notes and the assignments for this week, okay? So we have a couple minutes before start. Does anyone have any questions or anything? No? I posted an internship opportunity that I've been working on this for a while. So the 10 interns that are applied, we had 2 working. We actually, after the qualification, there were actually 8 of them, not 10. The next 6 is getting ready to be working for the next 2 companies. And I have my internship running until next June. So if you are interested in applying and doing a part-time internship, this is different than the apprenticeship program that I've been doing. We have a few companies right now that are looking to hire programming students for the internship. And then if they like who the candidates would be, in the long run, possibly you could get a job with them. But this is mostly focused on the computer science and the cybersecurity with the Department of Defense. I added this in the announcement for you today. So if you're interested, you can complete the application. It looks like this. Okay. Make sure you complete all areas and attach your most updated resume. So it pays $15 an hour, and the grant actually covers up to 80 hours, and you can do at most 20 hours a week. And we are flexible with your schedule. So you will be working remotely, and you can start either this semester or sometime in the winter if you like. If you start later, then we will pair you up with the companies, and usually they would select the candidates. So we would send out your resume for the later terms if you like. The background check will need to be processed after your application is completed, and the resume will be sent to the company, and they usually would conduct a short interview. So they will meet with you and ask questions. We work with companies that's contracted or funded by the Department of Defense. The majority of them are building military base projects. So with that, students have to sign non-disclosure agreement in which you can't discuss the project with anyone else except for the company. And as a coach within the project, I do get to see some of the areas, but I also have to agree that I don't disclose that to anyone else. So some of the things that you might be working on, there's a lot of development in the virtual reality for military training, and also smart helmets, different areas with cameras, terrorist detections, sensors, stuff like that. So if you are looking to go into that type of area, it will be good for you. And then for the engineering and the software development students, you can also look into gaining additional skills, learning how to use Bash script. The majority of them are not at the security stage yet. They're still in developing, and then some of them are. So my security students, usually they work on putting together security plans and things for them. But the majority of the companies are looking for programming students. So if you're interested, you can complete the application. If you have any questions and you want to address that privately, you can send me or Joe Gonzalez an email. I coach on the technical side, and then I meet with the employers week to week basis. And then Joe, he helps with the business processes, getting application completed, and also timesheets and such. Okay. So if you have any questions, shoot us an email and you can check out the opportunity there. Okay. Any question? No question? Okay. All right. Let's talk about what we need to cover today, which is Unit 10. And originally I structured this prior to spring. It was in Unit 10, and then I moved it back one unit last spring. So we are going to cover the next chapter in the text, which is chapter 16. I have to edit some stuff from the lab as I modify some of the components, so I will release that hopefully tomorrow so you can take a look at it. And I'm sorry about the video last weekend. I had uploaded it, but then I completely forgot to click the publishing for the Zoom link for you guys. But it was on YouTube like right after class. So, all right, so let's talk about chapter 16. In Unit 10, Chapter 16, we're going to talk about graphs. And this is essential for us because you will see that in communication, in networking, in programming, in computer science, or even system development, you might be working on systems that need to communicate with another system or acquire data from another system, be able to sync with records, for example, like database servers. You can update on one server and then be able to sync it with other branches servers. In airline and transportation companies, you would see that mapping and graphs is really important because that would allow us to see, you know, if there's flights that's going to be on time or delayed, even with customer tickets and all of the areas that needs to go into transportation. So that's important in communications and networking, like routing. You will see some of this carried into routing. on how it would determine vector for distance, and also to really see the available routers. And that's how our internetwork really is established. And then social networks, if you're looking at Facebook, Instagram, and some of the social network sites, how they're able to store posts, videos, updates, etc. in various nodes. So modeling this is important, and you need to understand the discrete structure of it, how data is being transmitted, how it's stored, how to retrieve, access, and even evaluate data. And so this week we're going to go over graphs. So to start, we can touch on what a simple graph looks like and how to read the vertices, which is going to be how that's going to connect to the edge. So the way that we write this is that in a simple graph, we would indicate the first value, which is going to be your vertex, and the edge is going to be indicated next, and that goes into a parentheses or the brace. So now we need to know that in a simple graph, you would likely have the unordered pair of vertices, which contain two vertices. And with that, they would be connected to an edge. Now, if they're next to each other, for example, A and C here, we would see that A is adjacent to C. Okay, they're neighbor, they're next door neighbor. And A is adjacent to D. Now, A is non-adjacent to B because it has to cross through another node, which is C, in order to get to B. And sometimes you would see this, right, in business world, where we would have, let's say, corporate office or headquarter, and headquarter would connect to some branches, and then the branch would connect to the sub branches. But so the sub branches are not directly connected with the headquarter office. So in such case, you would see non-adjacent scenario. And we would see the same way with telephone communications, routing systems, and all type of different servers that we would connect in order to establish data syncing. So in here, what we can state is that an edge cannot go from one vertex to itself. So we cannot have an edge that's connecting to itself. So it needs to have a source and a destination. So if I wanted to connect C to B, right, I would use an edge to connect these two nodes together. And those nodes can represent systems, locations, right, geographic locations, etc. So what we would have is we would have the vertices, which are A, B, C, D, E, F, that's represented in this picture. And then you would have the edge to connect the vertices. And again, the edge cannot go from one vertex to itself. Okay, so it has to have one point to the next point, which is going to be the vertices. Any question?
What exactly does it mean when it says E is equal to UV or E is equal to V of U squared?
So the way that you write this, right, you can have two vertices, which is U and V, and they could be named anything. They could be A, B, C, D, E, F, 1, 2, 3, 4, 5, right? So this is just an identifier from one to the next. So you can write the edge as U comma V. So I can have an edge that's A comma C, right? I can have another edge that's C comma B. Those are the adjacent nodes, right? C is adjacent to B and B is adjacent to C. Okay. Now you can have that it's repeating. So in when I teach networking, I said that sometimes you would have a one-way communication that will be unidirectional, meaning that let's say that I have a one-way for A to send to C and that's it, but it's still going to need to have that edge connected, right? But what if I have bidirectional, meaning that A talk to C and C talk back to A, right? Like I can send and receive on both ends. So you would have the A and the C squared because it goes both way. So you do see that represented in many different applications. So the way that they have it written like this is that we know that it's going to go from U to V and V to U. And in routing and network and communication, that's essential because you do have some systems that's only going to send to everybody else. So for example, with that is like how you would listen to a radio station, right? You can receive their signal and hear whatever the host is saying on the radio program. So it sends out to multiple points, right, through the radio towers, but it's not receiving from your end, right? They don't hear what you say in the car or, at your house when you're listening to the radio station. So you do have some case scenario when it's broadcasting to multiple points. And then in other cases that it listens and broadcasts, it sends and listens at the same time. So for example, like if you're using Alexa, if you're using like, Google Smart type of appliances at home, um, you do know that they, a lot of the things is speech detection. So it's listening, but it's also sending information that you asked for, right? So in that sense, we do have a node that's communicating both ways. And a lot of the times graphs tied directly with communication servers, an easier way to really visualize how change. Okay. So in some cases, you're going to have just one way communication edge. And then in other sorry, I got dropped off right there, right in the middle. Yeah, so um and from I'm getting spotty internet. Sorry. Every other minute, so hopefully it's going to be a little bit more stable. So you do see some systems that can only send and not receive, and then some systems that can do both. And then you do see some systems that would only listen and not send, right? Receive and not send. So sometimes that will be drawn with the arrow for the directions, and then sometime that they will indicate it both arrows to illustrate that it's going to go both ways. So if we do see a solid line like this, it would represent that it could go either way. Okay. So any question with this?
And so I know it's bidirectional, but does order matter? For example, if they write V of U versus U of V?
No, that's why it states that it's unordered pair.
Okay.
So yeah, but okay, take that out of the aspect of just how the graphs is drawn. Okay, so the way that is illustrated here is very general discrete math like. Okay, now if you carry that concept into something more on the practical side, for example, infrastructure. Okay, looking at, let's say you become a system admin, or even on higher up, right? Like a chief technology officer, and you have to really plan out on how your system would, you know, transfer data, how it communicate, how it would sync, you know, with different servers. You really have to take a look at the hierarchy in the actual infrastructure. Looking at, you know, a lot of the companies are using like top-down hierarchy, where there is some form of order, right? Realistically, in the real world environment, we do know that there is some kind of order in how the systems would receive and send data, or how it would store the data. Even in that structure, you would see that, you know, what would be the main storage and how that would get distributed. um, and we would use more of a distributed environment, in such that it would be more managed and centralized, where you would have one system that's going to store, and then it's going to update all the other systems. And while the other systems are updating, it has to update the central point. So in such sense, right, we have to have the understanding that that is really the practical side, but the way it's drawn and written here is there's no hierarchy and there's no order. Okay, so when they write it like this, yes, it is an unordered pair of vertices. But when you're looking at the overall picture of all these nodes connecting together, right, you have to ask yourself, is there a weight, right? Is there a priority in specific nodes, right? How is the data is going to be communicating? And that comes back to the overall infrastructure on how you're using the data. Okay. All right. So question?
No, thank you.
Okay. Okay, so for this, I do see a chat. Let me touch on this. Okay, so for this, we would have A, B, C, D, E, F. Those are going to be the vertices. So when we list them, we simply look at these nodes, and you would list them like this. Now, to include the edge, you would say which node is connecting to which. So you would have AC, right? AD, because they are adjacent, and then DF and DE. Okay, then we can move, and then DA. So some node would connect to multiple vertices, right? One vertex can connect to other vertices, and then some would be one-to-one, as you can see. Okay, now BC or CB, right? So it doesn't matter how we write it, and we can only write it once and it would represent both. Now in the case where it's directional, then yes, you have to specify which direction it's coming from and where it's going to. And so you would have BF and then FE. So the non-adjacent neighbors, right? So A is non-adjacent to F. They're not next to each other. They don't directly connect. It has to pass through other vertices to get there. Okay. A is non-adjacent to E. Okay. Or A is non-adjacent to B. Okay. So A is only adjacent to D and C. Okay. So here what we can do is look, here we only listed a couple that are adjacent, right? Like D and F is adjacent. C and E are non-adjacent. So that shows you a couple of the example there. Okay, any question? Okay, so let's take a look at another example. Okay. So here it talks about this prior graph, the graph from 16.1, which is a simple graph. And we see that A, B, C, and E have degree 2. What do they mean by the degree of 2? It's because A is connecting to 2 other nodes, 2 other vertices. A is to D and A is to C, right? And then B also is connected to C and F. So it has 2 degree. Okay. Now D has 3 because it's connecting to A, it's connecting to F, it has another edge to F, and it has a third edge to E. Okay. Now, in a sense, you can also see this being applied in like shipping, for shipping company to really route shipping, like for FedEx, UPS, etc. Or in the case where we can graph out, transportation, like for the 18-wheelers that's delivering shipment to stores, like for Costco, Walmart, Target, grocery stores, etc. So you do see graphs being used for different cases outside of just communication and even social networks, right? So the way that we look at degrees is we should ask ourselves, how many other vertices is my source connecting to? Okay, like I said, D has 3, okay, F has 3 because it has the 3 edge. That gives us the degree value. Okay. All right. So here is the explanation. It says, note that the length of the path of the number of edges in the path is going to give you that degree. So we should count off the edges that are connecting to that node, and that's going to give us the value for the degree. Okay. So here is another example, right? So you have ACBF is a path from vertex A to F. So if we're looking at how we're going to be able to go from A to F, right, we can do A, C, B, F. Okay, so A needs to connect to C, C needs to connect to B, and then B connect to F in order to get there from A to F. Okay, and if we're looking at the path from F, right, to D, we can go directly from F to D, or we can do F, E, D. Okay. So I'll give you the perspective of this in routing. Let's say that you are connecting to the internet from your home router, and your home router is connected to your service provider routers, right? And they, like whether you're using Spectrum, Frontier, or another service provider, they have a group of routers in between in order to get your request when you're visiting a website, right, to the web server. So what happens is that sometimes, right, we would be able to directly submit that request, okay? But the majority of the time, you're going to have routers that are occupied, or and other routers are available, okay? So what the other routers would do is it's going to say, hey, pass it to me, and then I can get it there. And so in order to get it there, it has to pass through the other routers in order to get to the web server, like for Google, or a website, or like YouTube if you're visiting those websites. And then the web server has to acknowledge that it sees your request, and it has to send back the acknowledgement saying, okay, yeah, here, I acknowledge that you're requesting this. I'm serving you the HTTP right? Or HTTPS request that your system is asking. So it has to send back, and on the way back, it could go through multiple points instead of directly to your system, and likely it won't. And that's how our internet really actually works. So sometime you would have to pass it through the in-between nodes because you are not adjacent to that other node, the destination node, okay, or the vertex. So from here, what we see is that you do, when you have an edge, you can have a path, but sometime that you would have to connect to the adjacent vertex in order to connect to get to the destination node or the vertex that you want to go. Okay. So when we say if it's a long path, that means that we would connect to other nodes and sometime in repeats. And if we're looking at like internet traffic, sometimes that would pass back and forth because it's based on the availability. The whole point in transmission is to get certain type of traffic to that point quickly, right? So if you're downloading from a website, all of this is happening. So we might see a long path if we really map it out. So we can go from D to A to C to B to F back to D and then send it back. Okay. The whole idea is that it should not come back to the source, but it should go to other entity, other routers in order to get to the destination. So you might see some repeat, or sometimes when you get there, that system is busy and it's just going to pass on to the next. Okay. It would time out because it's occupied. And in the case where if you're looking at like dedicated line for communication, where let's say that I have the Department of Defense and they need to communicate with a certain military branch, what they can do is they can specifically set up a path of communication where it's only going to be specifically for that purpose. So you might see a short or a long path. And in a simple path, sometimes we would be able to pass it across multiple nodes in order to get to the destination, as we said. Okay. So here is another example, and it shows you how you can write that out. So we would start with this type of problem by listing your vertices. Okay. We have A, B, C, D, E, F, G, H, and I. And notice that the I and the H is not connected to the rest. Okay. Now, how does this really apply to the real world, right? How does this really apply to what we see in the technical world? Well, you do have some isolated systems, right? Systems that would be used for sandboxing. For example, you might work for a company that's doing testing on malware or testing on certain type of tools and software. And we don't want the test results to really impact the other systems, right? Let's say that you would test different source code here, or when they're engineering something and it's not ready to roll out live, right? We can set up it in an isolated environment and then to be able to implement it, right, once it's ready. So you have the H and the I isolated from the rest, okay? But we still have to list them because they are vertices and they have an edge, okay? But they will be non-adjacent to the others, okay? The only thing that they're adjacent to is themselves, right? H is adjacent to I and SI is adjacent to H, and that is it, okay? Any question? Okay. So here it shows you and it gives you the definition, right, of what is a simple path. So you would have a path that has no repeated vertices. Okay. So if we're looking at, let's say that I'm looking at going from A through F again, if I go A, C, B, F, that could be a simple path, right? I don't repeat the same edge. I don't go back and then redo it again, right? Or I can go A, D, E, F, right? I can go the other way, or I can go A, D, F, okay? Now, if you have repeating edge, then it cannot be a simple path. So let's say that I can go from A through F by doing A, A, C, B, C, B, F. Then it won't be a simple path because you're repeating the B, C edge multiple times. Okay? Any question? Okay, so now if we're looking at this image, we would see that there's certain things, sometimes you have no path, okay? So we know that H and I, they're by themselves out here. So you have no path between E and I or F and I. So the others are not connected to H and I. So you don't have a path with D and I or D and H and so forth. Okay. So with that, I think we are good to answer some of the questions. Oh, and one more thing. A cycle is a closed path or a loop that has no repeated vertices, okay? Except for ending up where you start. So if you're looking at the cycle, it's exactly what it means. If we're looking at this picture right here, right? I can go A, D, F, B, C, and then back to A. That's a full cycle. Okay, I didn't have any repeating edge there. So I can go this way and then come back to A. Or in the case of D, I can go D, E, F, and then back to D, and that's a full cycle. Okay, so let's answer the first question. So you have this picture, okay? And let me shrink this a little bit so we can see. Okay, and this is the graph that we're given. We want to first list the vertices, then B, we're gonna list the edges, and then C, we're gonna list the degree of the vertices, and then D, we're gonna say which one's adjacent, which one's non-adjacent. Okay, so I'm gonna get you started with that. So it tells you to refer to, hold on one second, I think I have. Let me open up my instructor file so you can see what I listed here. Okay, so for the first one, let me put it on this other file so we can start listing, and this can get a little bit tedious, but we can have some practice right now. Okay. All right, so now we can see it. Okay. So for 1A, we're gonna start listing all the vertices, right? I just keep it from A through G, but you can start with B and then going forward. That's fine. So I list, there's A, B, C, D, E, F, and G. Okay. These are the ones in the round shape there. Those are your nodes. And So we would list the vertices. Then we can start looking at the edge. Which one is connecting to which? Okay, so I know that there's B to A to start and then B to G. Okay, so I have BG, BA, A to E, A to F, and A to C. And then A to B. So A actually has 4. Okay. And then next we move to the right, we're going to go to C. C is connecting to F, to A, and to D. Okay. So I have CF, CD, and CA. And then we move over to D. D has 2 degrees. So D to C and D to E. And then next I move over to E. Right here. E has 4. So E to G, E to F, and E to D. I think I listed EG twice there. And we can move to F, F to E, F to C, F to A, and then after F, we would continue with G, and that will be GB, GE, and GF. Any question? Let me mute my video so hopefully I can stay on longer. Any questions? Okay, so once you have listed the edges, then you can count up for the degree, right? How many edges, each of the edges is going to represent 1 degree. So if we're looking at A, we have 1, 2, 3, 4. So A would have a degree of 4. And so is E. And so is F, right? There are 4 lines connecting to it. You have 4 edges. And then for C, we have a degree of 3. So it has 3 edges. And then for G, we would have 3. Okay. Now the lower ones are the B and the D. So you have 2 for B and then 2 for D. So you're expected to know how to look at a graph and how to be able to see, right? Which are the edges, how the edges are connected to the vertices, and the degree for the edges. Okay, and you would see something like this on quiz and final exam. You will be given a graph and you have to be able to determine, right? Adjacent, non-adjacent, vertices, edge, and so forth. Okay, any question with number 1? Okay, let's continue and answer some of the next few questions in 1. So next we can list adjacent and non-adjacent vertices. And here you don't have to list everything. That's fine if you list a few, that's okay with me. I wanted to make sure you know how to see what's adjacent and what's not. So we can say that B is adjacent to A and G. Okay, B is connecting to G and it's connecting to A. So they are adjacent. It's not adjacent to E, however, right? It doesn't connect to E. Okay, but it does have a path to E. So we can go BGE. Okay, B is non-adjacent to F, to C, to D. Okay, so that's what I list. I list that B is non-adjacent to E, F, C, and D. And then we can look at A. A is adjacent to E. It's also adjacent to F, and it's adjacent to C, and it's adjacent to B. Remember, it has 4, right? The degree of 4. So that means that it should have 4 adjacent vertices. Okay. Okay, and then we can say that A is non-adjacent to G and D, right? Because A needs to go through C to get to D, and A needs to go to A to get to G. And we can look at E. E is adjacent to A, D, F, and G. So it's next to A, to G, to F, and to D. E is non-adjacent to B and C. It doesn't have an edge to those. Okay, any question? So here I listed C. It's adjacent to AFD, and it's non-adjacent to EBG. And then if you want to do all of them, this is what it would look like. So I have D there, adjacent to C and E. D is adjacent to F, A, G, B. And F is adjacent to E, G, C. F is non-adjacent to D, A, B. And then I also listed G, which is adjacent to B, E, F, and it's non-adjacent to A, C, D. Okay, any question? Now, sometimes, right, we will not have just 7 or 8 or 6 or a few. We would have lots. And if you're looking at for a large enterprise, that could be a lot more. You would have thousands of servers, you would have hundreds of communication systems, and such. So the whole point in this is to be able to identify, right, if we have an edge or a path to from one point to the next. Okay. Question, I see some chat. F is adjacent to A for number 1. F is adjacent to A, yes. Sorry, I think I had that mistyped there. F is adjacent to A. Yeah, because it has 4. It's not adjacent to B and D. Okay. No other questions for number 1? Okay, so let's look at the next one. I listed some of the degrees in the first part, but we can repeat. So if you listed it up here, right, like what I have, then that's okay. Okay, so okay, so for the last part, we simply just need to list the path. Okay, first we can list the simple path. And notice that the simple path doesn't repeat the edge. So we can start with B going into G, right? And then you can do B, A, E, G. Let's say that we need to go from B to G. So we can go directly from B to G, or we can go B, A, E, G. Okay. And then we can do A, E, F, C, D. So we can go A, E, F, C, D, or we can do A, C, D. Okay. And another option we can do is we can do C, F, E, A, B, C, F, E, A, and B. Or we can do C, F, G, B. So there are many ways that you can set up the simple path in this one, since there's no requirement from where to start and where to end up. So you can just list any of the simple path is okay. Can I do a long path? Anyone wants to do a long path? So we can include all the nodes, right? If you wanted to do a long path, then you can go all the way around. And then if you go back to the beginning, then you have a cycle. Okay, so Albert suggested that we should do BA, so BA, C, D, E, F, G. Yeah, that will be a long path. Okay, visiting every vertex. Okay. And if you go back to B after that, you have a cycle back where we start. So some of the smaller cycles, so let's take this one, E, F, G, E. So I can do E, F, G, E back to it. Or I can do B, G, E, D, right? E, D, A, B. What happened? B, G, E, D, C, A, B. Missing one there. And we can have A, C, D, E, A. A, C, D, E, A. Okay, so the cycle would get us back to to where we started. So you can list any of the cycle, that's okay. Any question? Okay. All right, let's look at number 2. This is similar to the example that we see in the notes in the text. Okay. So we would first with 2A list all your vertices. Okay. So I have A, B, C, D, E, F, G. Now, these edge, there's no weight to it, right? Like we just assume that it would be 1 where they will be all equal. Sometime you would see graphs that would have number on the edge, and that will be the weight for that edge. Okay. And in the networking world, I'm more familiar with that because that's really the beginning of my career, right? So we would use those values for like vector distance, so you can set your communication systems, like your routing system, to have specific path based on the weight of that path. Okay, so we'll talk about the shortest path, the cheapest path, and all of that in a little bit. So if you don't have any number on the edges like these, just assume, we can make an assumption that that will be just 1. They're all equal in size. Okay. After we list the vertices, then we would start listing the edges, right? We can have B to A, B to G, A to G, A to E, A to F. And then you can do E, G, E, F. And then we have the C and the D by themselves. So once we have the edges, we can count them up, and that will give us the degree. So for the E, you have 3, as it has 3 edges. And also F has 3. A and G has 4. It has 4 connecting edges. C and D has 1. So the way that we would write it, you would see it like this. So you can list the edge and then put the superscript to indicate that that's the degree. Okay. So I can say that C to D has 1, right? They're only connecting to each other. Okay. And then you have B, for example, B has 2. In our assignment, B has 2. Okay, any question? All right, so after part C, after you listed all the degree for the vertices, then you can list the adjacent and the non-adjacent. So I started with B because it's in the corner. So I have B is adjacent to A and G. B is connecting to G and B is connecting to A. B is non-adjacent to E, F, C, and D. So E is not directly connecting to B or F, right? And then C and D, as they are by themselves, right? We have no non-adjacent to B. And C doesn't have a path to B either, nor D. Okay. Okay, and we can continue to list the adjacent and the non-adjacent for our vertices. C is adjacent to D. I recopied it so I could see it because as it dropped on the next one. Okay, so you can list the adjacent and the non-adjacent for, if you like, you can do all of them. The majority of them is okay. It gives you practice. Now, when we put this into a matrix, we cannot skip, because if you skip, then you're not going to have the right result, right? So while it seems very tedious, you should identify all of them, the adjacents and the non-adjacents, because if we don't have an edge, we put a 0. We have an edge, we put a 1. And that's how we can build the matrix. Okay. So after I list E, F, and G, then I can specify the degree of vertices if I didn't do that earlier. So when you see a graph, start with listing the vertex, then identify the edges, then identify the degrees of the vertices, then identify the non-adjacent and adjacent, okay? And then identify the path and the cycle. Any question? Okay. So after we have the adjacent, non-adjacent, and the degree information, then we want to state the simple path. And you don't have to list all the paths. You can just pick the ones that you want to start with and where you want to end up. So I chose the BAFEG, or you can do one from C to D. Okay. Then I can have a cycle where I can start at one point and then come back to it after it goes through the other vertex. So you can list the path and the cycle there. And in this one, what we can do is we can point out that there's a no path, right? Because you have the C and the C and the D by themselves isolated. Then we can say that there's no path between C and F, C and A, C and B, C and G, and C and E. And then also we have no path with DF, DA, DE, and DB. Oh, I did put it down below. Okay. And then we can create a long path. So I went from B, I go to A, and then I go to G, E, right? G, A, E, F. Any question?
How exactly
Okay.
does a long path differ from a simple path?
So a long path, you can have repeat of vertex. Like in this one, I have G twice, A twice, right? So it can sense it and sends it back. So once it receives it, sends, come back, and then send again. And then I have E twice. While that's not really, I can't say that it's not efficient, because if depending on what we're looking at, but yeah, while that might seem like it's not, sometimes that for the sake of time, because based on the system availability, or sometime that it needs to receive additional information from certain source, you would have a long path. Okay. Like if we're looking at like updating of or syncing data, okay, because if you have multiple sources like this, sometimes that they subcentralize it, so you have B going to A to G to E back to G, because G is connected to the other one and it would sync the data from there too. Okay. And then sometimes it's also for availability reasons, because we can't really predict, like we can predict a lot of the times as far as like traffic or, the amount of workload that these systems are committed to. But sometimes that you would have a peak in it, or sometimes that will be lower. It all depends, right? So you wanted to be able to get data transfer across even when it's peaked or when it's low. Okay. Question. So simple path, no repeat of vertex. They all have to, it's only one time. Long path, you can have repeats. Okay, so that would conclude number 2. Okay. Okay, so sometime we would have a mix, right? And you would have something that can be both ways and something that's only going to be one way. And in such sense, you have to follow the direction on how that would be connecting as edges. So, sorry. So in number 3, the yellow path or the yellow edges really illustrate directional. And then the green one, it can go both way, right? And then sometime you would see it drawn with double arrow. Okay, one on each side. That means it goes both way. Just like all the other ones, for number 3, we would start out with our vertices. So list all your vertex here, the vertices. So I start with A and I went all the way. So A through G. Then next, we can start listing the edge. Okay. Now, unlike the other ones that we looked at, this one, B cannot go back to A. Okay. A can only go to B. B can go to G and G can go back to B. So in this sense, we're somewhat limited compared to the other graphs. Okay, because we would have specific way to start and go forward. Okay, so I list A, B, A, E, and A could not go to F, but F could go to A. Okay, then you have BG, GB, of course. Okay, now E can go from E to G or E to F, but it cannot go from E to A. So my question for you is, should you still consider that they are adjacent if it's only a single direction? So the answer to that would be, if you have from A to E, it's still an adjacent, right? As we would have one edge. Okay. So A would be adjacent to E. E would be adjacent to F. E would be adjacent to G. Okay. Now, if I need to go from G to E, I have to go from G to A to E. So that becomes a non-adjacent from if we're looking at the other way, right? So I can say that E is adjacent to G, but G is not adjacent to E in this sense, because we cannot go the other way, right? So that means that if I start at G, if I want to go to E, I have to send from G to A and then to E. So once you list all the edges, then I want you to identify the degree of vertices, and you have to do this on your own. Okay, I started the first 2 for you. So count up the edges and look at the direction of the edge. Of course, in this one, it's different. And then we also want to identify the adjacent and the non-adjacent vertices. Okay. Then we need to list the simple path, the no path, the long path, and the cycles. So a good cycle that's a short one is A, E, F, and then back to A, right? Or you can do B, G, A, B. We can do a very short, simple path like C to F, or we can do C, F, D, okay? Like if we want to go from C to D, we can do CD or CFD. Two ways. And then you can specify the long. Any question? Okay, so make sure that we answer these. Just look at the graph and be able to list them. Okay. All right, while you're working on that, I'm going to flip back to the notes and make sure that I cover all the details that I need. So on page 2, it shows you how to read the path in blue. We talked about that. So next we're going to talk about weighted graphs. So when you don't see a value next to the edge, as we said, we're going to treat them as all equal. And the way that we build this is that if you don't see a value, you just treat them as 1. Okay, and then the absent of edge is going to be 0. So now in some graphs, you would see an edge that would have a value. And so that means that there's a weight that's associated with that edge. Okay. And why is that important? Because we want to be able to, we can set this value to be priority queues. So for example, I can put a value to specify like that's higher in importance level compared to another edge that's not. Okay. And so it can be used in many different ways, but that's just an example. So in a weighted graph, it would look something like this, where you have A to B is 7, B to E is 2, and so on and so on. And then some edge, you would see that they are equal in value, right? You have the same weight for D to H and B to E here. Okay. And we can use the weight to really determine specific path, which is going to lead us to that. So what we can do is we can look at the total weight of a path in this example. What we can do is we can take each of the weighted edge in that path and we can add it up and we would get a value. And you can use the total value for a specific path to compare it with the total value of another path. So if we're looking at, because sometimes you might have less vertices, but the weight, the total weight is higher, right? And if you're saying that higher is worse, right, in that case, then so sometimes you would have, you know, more or less vertices and you would have different in the weight because some of the edge have different value, of course. So here what we did was we have ADHKO and we would add up each edge weight and we would get 16. Then when we look at another path, EDHK, okay, we start with E and we go to K. And a second path, we start with E and we go to K, but on this one, you have more vertices. You go from E to C to F to L to O and then K. So what we can do is we can find the total weight and compare it. Okay. So we see that if we go ECFLOK, that's going to be 24. In comparison to if we go EDHK, that will be 12. Okay. And as you can see, this is often used looking at things like airports, okay, like route flights, trains, you know, train tracks, stuff like that. So we can look at how planes would stop at specific airport or connecting to a specific airport. Or if you're looking at shipping and package delivery, right, you can see which warehouse or location that it will pass through before it gets patched to the next group of trucks that's going to transport the shipping packages. Okay, any question? Okay, so in the weighted, we see how that would work. So often, you know, what do we really get out of all of this is that the whole point in creating the adjacency list, looking at the vertices and the edge, finding the adjacency, is to really build the adjacency matrices. Okay. If it's not weighted, we just use one that it has the edge. If it's 0 for none, right, or adjacent, adjacent is 1 and non-adjacent is 0. Now, if it has the weight, then you use each of the edge weight value in your matrix. Okay. So when you do the lab this week, you're going to see something like this on how we, because the way we program is, yes, we can say that, okay, this node, this node, this node, and this node, all we do is we just create an identifier, right? And then we would say that, oh, it's connecting to here, to here, to here. But ultimately, we want to build a matrix by looking at the adjacency to indicate the present of and the absence of edge. Okay. So from the programming side, we can implement matrix once we identify the adjacency to be able to possibly calculate the cost of that path. Okay, so just going back to what some of you attempted in the past, which is travelers to on the Hawaii Islands, right? Some of you built the matrix for that and you calculated out. But back then we were working on the probability. So you do see movement, and we can even use this for, you know, the way that we graph out, right, transition with COVID-19. Not just looking at the statistics side, but just to look at how it's spread and how it's contained. Okay, so there's a lot of different applications in this. So here on page 5, it shows you on how to be able to look at, you know, the weight and put in the weight into the matrix. And I'll show you how I implement it, because the way it's drawn here, it can be difficult to kind of visualize and see. Okay. So now for the matrix, what you can use is you can use multidimensional array, right? We would usually implement the 2-dimensional array, and then we would represent using a linear functions for the n-dimensional space. Okay. So, and often you see, or they talk about the example with computer graphics, but there's many application on how we would use graph with matrix for different purposes, and I gave you those examples. Okay. And so we would write it like this. Now, when I do this assignment, I just use a table because it's easier for me to visualize it in a table format, right? Yes, you can write it in this form if you like. Okay, so let's move forward and answer the next question. What I should do is to create individual page for these things. Okay, so let's build the matrix for this with the adjacency, right? So now you can write out the adjacency list, but what I did was I went ahead and you create a table here so I can illustrate this to you. Okay, so we know that we have vertex from A through G, right? So first thing, we need to identify our vertex, A through G, and then A through G for the column and the rows. Okay. Then earlier you had saw how it's defined. You don't have an edge that's connecting to itself. So from A to A, we're going to put a 0. There's no such thing. It's absent, not there, nada, right? A to A is 0. Now A to B, since there's adjacency, we would put 1. Okay. And then A to C, we have A to C, we have 1. Then next, we're going to go from A to D. It's not adjacent, right? It has a C in between, so put a 0. There's no connection to E either, so it's not adjacent, 0. A to F, none, 0. A to G, yes, 1. So the easiest way, you know, extra work, however, we would start listing the edges, and from the edge you can fill in your matrix, and that's also quick. Okay. Next, we're going to do B. B to A, yes, 1. B to B, none, cannot connect to itself. B to C, 0. It's not adjacent. A is in the middle. B to D, 1. No, I'm sorry, 0. I'm in the next row. B to D is 0. B to E, non-adjacent, 0. B to F, 0. F is over here, B is there, so no. B to G, directly it has an edge, so it is adjacent, so yes, 1. And then you would continue with the next one, C to A. So C to A, yes, 1. C to B, no, 0. C to C, of course, 0, not to itself. C to D, 1. Okay, here's C, here's D. Then you have C to E, 1. C to E. C to F, 1. And C to G, 0. E is in the middle. Or F is in the middle. So no. Then next we do D. D to A, no, 0. D to B, no, not adjacent. D to C, yes, 1. D to D, 0, not itself. D to E, no. Okay, no. D to F, yes, 1. And D to G, 0. Okay. Then you would do the E. Okay. All right. So E to A, 0. E to B, 0. E to C, 1. E to D, 0. E to E, none. E to F, 0. And E to G, 1. Okay. And then you can do F and G. So if it does have an edge, put 1. If it doesn't, if it's not adjacent, put 0. And it cannot connect to itself. Okay. Any question? Okay, so we cannot really build a matrix, right? Adjacency matrix without the adjacency list. Okay. Knowing which one is adjacent, that's going to help us build the matrix. Any question on this assignment? This question? Okay. Move this up as I adjusted the answer here. So this one, the next one we're going to do is weighted. Okay. So unlike the other one, when we fill in the matrix, we got, so number 4, you use 0 and 1s. On number 5, you have to use the weight. Okay. So let's start again with some, so I'll start you build for the beginning for you, and then you just have to fill it in, the rest. Okay. So this one we have A through G for the vertices. So your vertex A, B, C, D, E, F, G. Okay, so as it's 2-dimension, we got vertex A, B, C, D, E, F, G. Okay, so both for columns and rows. And just like the other one, we can start with A. So we have A to A is 0. A to B, I have a 3. So I put 3. Okay. A to C, I have a 5. So put 5 for the weight. A to D, since it's not adjacent, put 0. A to E, not adjacent, put 0. A to F, not adjacent, put 0. Okay. And then A to G, it has a weight. It's 8, so put 8. And then next we can do B. B to A, it's a 3 right here. B to B is none, 0. B to C, not adjacent, 0. B to D, not adjacent, 0. And B to E is also 0. B to F, not adjacent, 0. And B to G has 7. So put 7. Okay. And then next we will do C from that graph. So C to A is 5. C to A is 5. Put 5. C to B, not adjacent, so 0. C to C, 0. C to D, there's a 4, so put 4. C to E, there's a 6, put 6. C to F, put 4, because it's a weighted 4. And then C to G, not adjacent. It has to go through E, so put 0. Okay. Then we can move to D. D to A is 0, not adjacent. D to B, 0. D to C, 4. D to D, none, 0. D to E, 0, not adjacent. D to F, it's 5. And D to G, not adjacent. Okay. Okay, so I got you started from A through D on number 5. So you have to complete the rest from E to G. E, F, and G. Any question? Okay, so our goal is to fill up the matrix here for number 5, right? If there's a weight, put in the weight. If it's not adjacent, then put 0. So there's some example on this, also on how to complete this matrix, right? And you can put it into the matrix format like this. I just use a table because I can tab and fill it real quick. However you wanted to do that, that's fine. Okay, and this is on page 6. You can also find that in the text. And then here's the weighted one on page 7. Okay, so let's talk a little bit about graph traversal. It says to traverse a graph, you must visit all the vertices of the graph by following the edges. We want to be able to do this in a systematic and efficient way. Okay. A solution to this problem would allow an airline inspector to fly to every airport a company flies to, right? Subway aficionado to take the train, every stop to the city, or the network administrator send message to every computer on the network. So you can start at any vertex, visit all the vertices by following its edge, right? Not necessarily. So you can only visit the vertex in a connected component of the start vertex. So what does that mean? Okay, so if I'm looking at this graph, I can visit from A, I can visit C and I can visit B, right? And then from there, I would go forward. I cannot go from A to D because it doesn't have an edge. Okay. I can go from A to C and then D. So what happens here is it's saying that you have to start, if you're starting at a certain vertex, you can only go to the vertices that are connected to it. Okay. To visit all the vertices, every vertex must be reachable from every other vertex. And that's important. So if we say that the graph is connected, we will look at 2 methods of traversing with both graph. So we would have a for traversal and for finding path in 2 vertices. So these are the type of traverse. So you have the depth first search. It's going to move forward from the starting vertex, and you can go as far as you can without repeating a vertex. Then back up one edge and look for another vertex to visit. Okay? And this is what we see when you back up one, that's really a recursive. Okay, so in the algorithm implementation, because the way we would represent this in programming, it's all at abstract level, right? To represent the physical system on how it passes from one physical system to the next, then what we have to think about is our starting point, we can only go to the connected vertices from that starting point, and we want to go without repeating any of the vertex. Okay, then we're gonna back up one edge and look for another vertex. So if I back up one, I can go another way. Okay, so here okay, so that would be a search. Now for the first, with the first depth traversal, what it's telling you is you need to find adjacency list or create one, and that's going to guide the search. So the search is going to use depth first traversal for the search. Okay, so that approach, we're going to use this. Okay, so look at this example. So we start with A, go to B, H, F, I, D, and what we want is we want to get to here. Okay. Now, what we can do is look, it can go this way to get to E, or we can go this way all the way here to here, back up one. Actually, we can't go all the way up to here and then go this route. No, yeah, I don't like the way they use this graph right here. So with A is that you have alternate connecting edge, right? If we go from A all the way down to E, what we can do is we can start with vertex A, proceeds to B, then only vertex B lists the H. So at this node right here, right, it's going to be able to say, okay, it's going to send it to H because at this point, B is going to contain H information. And you see this in router, even if you're looking at like nodes, right, on where the data is stored. A would not know about H. A would have to rely on B to get to H. And in order to seek, right, the data at one end, it's going to have to refer to each one of them to be able to get to E. So it says that the first vertex on H list is B, which already has visited. So the traversal proceeds to the next one, which is F, and then I, and then D. Okay. So the first vertex on D list is A, which already had visited. So the traversal goes back to C and then E. Okay. So as it could reverse, it would traverse and then it's going to go to the next one. So D has information about the previous vertex. So it's going to send it to C and then E. Okay. Any question? And this is also a way that we can also map out, right, how the system would be able to retrieve data. There would be a lot of different type of use in that, of course, as the book also give you some example. Okay, so here is the depth first traversal. Here's another example. Okay, this one's a little better. So you have A, B, H, F, I, C, D. Okay, so we're going to go from A to B, okay, to H, to F, to I. Now, why did they list the D, the C, and the E? Because alternatively, A also contain information about what? The next node, which is D, which is C, and then E. Okay, so A, that first traverse starting at A, and what it's going to do is going to visit the nodes in between. Okay, so that means C, D, I, F, and H. Okay, before it gets to E. Any question? Okay, so that's one type. Okay. The second one is your breadth first search. It must visit all vertices that are adjacent to the starting vertex. Then do a breadth first search from all of those. okay? So here, it gives you the explanation here. You're starting at A, then you're gonna visit the A's neighbor in order to build the adjacency list. So from A, we know that A is adjacent to F, to B, and to D. At that point, we have to visit all the A's neighbor, AB, AF, AD, right? So we have to visit B, F, and D. Then it says, then visit the neighbors of B that have not been yet visited. So that means H, okay? Because you have to go to A, B, and then the neighbor of B, which is H. And then also the unvisited neighbor from D, which is C, E, and I. Okay. So at that point, all the vertices have been visited and traverse is complete. So the whole point about traversing is to gather, right, information all about the other nodes, not necessarily adjacent. So we start with adjacent, and we would use the neighbors to gather information of all the other vertices. Okay, so with the breadth first traversal, it operates from that starting point to the adjacent. Then it's gonna do a first search traversal to gather information on all the other vertices that have not been visited. Okay, you guys ready to do the next one? Any question? No question. Okay, so let's talk about the next question. You can do the matrix one, right? So do number 6 and 7. If I have time, I'll come back to that. I'm going to address number 8 and then I'll come back to those. Okay, so for 8, it asks you to identify the depth first traversal path based on the adjacency list of the graph. Okay, so on this one, I'm going to start at G and I'm going to go to E. Okay, so what I'm doing here is if I start at G, what I'm going to do is I'm going to go to A, which is the neighbor of G, right? The adjacent. What A is going to do is A is going to have information about B, C, D, F, right, and E. Okay, because as each of the neighbor would have that. Okay. Now the other way we would also go from G directly to E. But it looks like we're simply going to go all the way around. But what happened is when you get to A is going to have information of all the other adjacent, and each of the adjacent would have information about the next adjacent. Okay, so I would have from G, I go to A, and A would have B, and B would have C. C would have information about D, and D would have information about F. F is of B, and F is of E. So when you get to F, you should know information about E. Okay. So now all of this, if we're looking from a practical, realistic standpoint, right? Whether it's routing systems, whether it's transportation system, tracking packages systems, all of these have updated. And once they already have that kind of update in each individual one, we cache that information. So when that route or that path get revisited again, it would have the information so it can quickly traverse. Okay, question. So of course, when you're looking at one way, alternatively in the traverse first path, you also have to look at, right, what is the other alternative adjacency. So your alternative will be just directly to G and E. Question. All right, so for 9, let's do a breadth first traversal. Starting at vertex F, illustrate any path on the graph, demonstrate the shortest path. Okay, so this one. So for 9, we can say breadth first traversal from F. We start right here. Okay. We can go to F, E, and E to B. Of course, here it's going to go C and D. But F can also go to B to C and D, right? Because alternatively, you have to have an alternate route because at the breadth first, it's still going to do search first traversal. So it's going to search up the alternative route, which we list in the any path. Okay. So the shortest path in this one, since it's not weighted, what we see is that the shortest path is the one that has the fewest vertex. So we can do F, B, C, D. Instead of going F, E, B, C, D. Any question? Now, if you have a node that have 3, 4 degrees in the breadth first traversal, you have to look at other alternatives and its path to really get to the destination. But the path of the alternative, we also want to point out any of the vertex that it has not been recognized or travel or crossover. Okay. Okay, last one, 10, and then we finish. So here's the weighted one as I explained earlier. So on this one, you can pick any path you want, but I chose to do F to B for illustration. You can use the same if you like. So I want to go from here to here. So I can do F, E, A, B, and I add up the weight, and that's 8. F, right, E, A, B. So 4 plus 2 plus 2 gives me 8. Then alternatively, we can do F, E, G, A, B. And when we add up those weight, we would have 21. Okay. Or we can do F, G, A, B. Okay, so F, G, A, B. So 6 plus 7 plus 2, that's 15. And then the fourth path that we can take from F to B, we can do F, D, E, A, B. So that gives us 18. The one with the smallest value in total will be your cheapest path, which is the first option that we stated. So know the difference between the shortest path and the cheapest path. Okay. Look at the example again and the questions for traverse, because they will show up on your quiz and exam. We'll talk a little bit more about the project going into Thursday. And then next week, as we still have some lecture, you can start looking into how to, you know, maybe work with another person. If not, work in teams. Okay, type in your name. Rogelio already started for you. Thank you. In the chat, in case, but I do pull the log for Zoom. Okay, do you have any questions for me? If you missed the beginning earlier, I think I was talking about the Cascade Catalyst, which is an internship that Joe Gonzalez and I have. If you're interested, we opened this and it's an announcement. I'm getting ready to get the next 4 to 6 that's going to be working. They already applied. So we're interested in bringing on a few more. So each company can only take 2 to 3 students. And right now, outside of some business students, they're looking for programming and security students. So if you're interested, here's the information for it. Okay. And then we'll try to match you up based on your qualifications and what they're looking for. So if you want to be part of that pool, you can apply. Okay, have a wonderful night. I will see y'all on Thursday. It's my birthday today, so I'm gonna get off, have a fish taco, and then watch a little bit of TV, post attendance, and go to sleep. So have a good night. Bye, everybody. Thank you. Thank you. Take care.
Happy birthday, Professor. Have a good night.
All right, good night. Bye.